My name is Josh Keaton. I work for NOAA Fisheries in the Alaska Regional Office in Juneau, Alaska. And the title of my talk is Halibut Avoidance Areas. I'm going to discuss spatial methods to reduce halibut incidental catch in the Bering Sea. Still technical issues, sorry. There we go. All right, so first you need to know what a Pacific halibut is. Pacific halibut is one of the largest flatfish. They grow up to be over 8 feet long and over 500 pounds. They live along the North Pacific Ocean from about mid-California all the way over to Russia, primarily in the Bering Sea. They are a sustainably managed species, and there's a vibrant commercial and recreational fishery, plus they taste good. So because they're such a vibrant commercial and recreational fishery, there's quite a bit of controversy over bycatch. And what bycatch is fish that's harvested incidentally, not a target species. So as other fishermen are harvesting their fish, they encounter halibut, and those halibut are considered bycatch. And halibut has got extreme cultural importance in Alaska. It's been harvested by Alaska natives for over 100 years, or for hundreds of years. And it's also important for subsistence, meaning that a lot of households go out and harvest halibut in order to fill their freezers to feed themselves. There's also, it's very economically important that the directed halibut fisheries support many coastal communities, both the recreational and the commercial sectors. However, halibut is, as I mentioned, a common bycatch species, and it's considered a prohibited species, which means any bycatch of halibut must be discarded with the minimum of injury. So, in order to control the amount of bycatch, it's managed with a limit, and if that halibut PSC limit is reached, the fisheries close. So, my study area focused primarily on the eastern Bering Sea and depths of 0 to 1,200 meters, and the data set I used is North Pacific Fishery Observer data. Most vessels that fish in Alaskan waters carry an independent observer that collects biological and spatial information, and it comes to us in that aspect of point data, haul retrieval, and a haul deployment location. And I used data from 2008 to 2014, and I limited this data, or this study, to Amendment 80 vessels in the Bering Sea, and I'll describe what Amendment 80 vessels is in just a little bit, but it accounted for about 76,000 individual point locations for that time period. So, what is an Amendment 80 vessel? An Amendment 80 vessel is one of 23 large catcher processors that operate primarily in the Bering Sea and Aleutian Islands, and they use non-pelagic trawl gear. And in the top right, you'll see a depiction of what a non-pelagic trawl is. Large nets that trawl along the bottom and catch multiple fish species. These vessels are large. They employ crews of up to 100, and they catch, process, and freeze their fish. They harvest multiple species, and their total annual harvest for those 23 vessels is 275,000 metric tons, or over 600 million pounds. In the bottom here, you can see a couple pictures of what an Amendment 80 vessel looks like. So, first thing I needed to do was group point data. Individual point data is confidential under the Magnuson-Stevens Act, meaning I can't give out location-specific fishing information. Point data estimates of rare species in which halibut is considered due to the sample sizes that the observers get are imprecise, and it's been suggested that you need to group those data to come up with more precise estimates. So, and then finally, grouping point data allows you to calculate rates for a given spatial area. And I used a hexagonal grid, and the reason I use a hexagonal grid is because of visual characteristics and that you get 6 immediate neighbors. And when you go into a hotspot analysis, the neighbors and the neighborhood is extremely important. I also, as I got into this study, I realized I was doing a lot of stuff manually and a lot of duplicate steps. So I ended up automating this analysis through creation of a quite large Python script. And on the right, there's a small snapshot of what that Python script was, but it's over a couple hundred lines. And it first groups the point data, and then it spatial joins that data to the grid that you choose, and it calculates the metrics, and that's what I'm calling the rate, or the halibut per metric ton of ground fish in a given cell. Then it gives the data pattern analysis, incremental global Moran's eye, which gives you what distance you should use as your search or in your neighborhood. And then it finally does the hotspot analysis. So a few things needed to be figured out in the data ahead of time, which was what temporal scale of analysis I should use. Well, fisheries change every year. Picking one year wouldn't be representative of all future years. You want to combine multiple years. And this figure shows that where fishing occurred in a given year changes over time. So what years to pick? Well, we know through exploring the data, the average halibut rate per cell was higher in years prior to 2011. I had a little bit of insight into the reasons why, and one of those is because there was a change in the management structure that occurred between 2011 and 2012. Prior to 2012, vessels were not, some vessels were not in a cooperative, meaning they couldn't pool their resources to, maximize their performance. And also there was smaller Pacific cod quotas. Now, Amendment 80 allocated species to each individual vessel, and if they reached that certain amount of or that limit, then they would close themselves down. So if you had a small limit on one particular species, you might trade off catching more halibut for less peacock. So I examined these data. I ran some statistics on it and found that there was no significant difference between the 2011 and 2014 data set and the 2013 and 14 data set. So we ended up picking the 2011 and 2014 data set for the basis years in the analysis. Then I also ran this data through multiple grid sizes. There's a couple advantages to using larger grids than smaller grids. Larger grids can be more representative of fishing activity. Remember, these are trawls, they're mobile gear. They aren't just fishing in one location. What I get as a point location represents approximately 19 kilometers of bottom cover. That's the average trawl distance that they covered, dragging their nets along the bottom. A larger grid also eliminates some of the confidentiality concerns of a smaller grid. However, with a larger grid, you end up with a larger footprint, and it overlaps closed areas. Areas where no fishing occurs shows as having fishing in it. And it also lacks precision in identifying local hotspots. Smaller grids are kind of the reciprocal of that. They're better at identifying the local hotspots, and they're more precise in their search distances, and there's minimal overlap in those closure areas. But because I have to still screen confidentiality, it results in more grids being screened. Finally, we get to the hotspot analysis on halibut PSC rates. As I mentioned before, I use the rate of halibut per metric ton in groundfish. Just plotting how much halibut occurred in each grid cell wouldn't be representative of where more halibut is. It's more representative of where more fishing occurred, but not where more halibut is. So I did this through multiple analyses, individual years and combination of multiple years, different target fisheries for the species, the predominant species that they harvested, and also in a seasonal aspect, picking out 3-month periods. And the results were actually pretty surprising. In almost all the analyses ran, they were pretty consistent in where the hotspots occurred. So I expected to see some minor differences in that, but that didn't actually come out. The same areas showed up in each hotspot no matter where, and I'll show you some of those here. So this first figure here is the hotspot analysis using the 5-kilometer grid. And so you can see that there's some areas down here by Unimac Pass. That's what this area is here, over here in Bristol Bay. And then these 2 islands out here are called the Pribilof Islands. And these are areas are known to have higher halibut, but they showed up in the hotspot analysis. Then you get to the 10-kilometer analysis, and you notice the same areas show up. So the grid size really didn't influence where the hotspots showed up. So after running multiple analyses, I tried to figure out, well, which one is the right one to use? And I decided that it would probably be better to combine multiple analyses and come up with an idea of what I'm calling halibut avoidance areas. And what these areas are identify those areas that have higher halibut bycatch, but also have the least amount of groundfish catch. So if you think about it from a vessel operator standpoint, a vessel operator would be looking, where could they maximize their groundfish harvest and minimize the amount of halibut bycatch that they occurred? So by using the different hotspot analyses and the different that I had run, I identified that I created two tiers of halibut avoidance areas. And tier one are those areas that were identified with high confidence in multiple analyses. And tier two were areas that were identified as having a high confidence of being a hotspot in at least one analysis. And these were usually the smaller spatial scales, but areas that identifying those local hotspots. And then I created a polygon feature class of those halibut avoidance areas to assist in the analysis of what that would mean in savings. And this is what you ended up with. So same areas that you kind of noticed in the hotspot analysis, these are just a little bit smooth and simplified so that vessels could use these to avoid halibut. And I went ahead and named them. Now each one of those I can then plot that North Pacific Observer data, which is the same data that we use for how much catch accrues to a given account, or how much fish is harvested, right? And I can plot how much came from each one of those areas, and as represented in the tables here, in all the areas. So, for example, if vessels were to avoid all the areas identified as tier one areas, they would save approximately 11% of their halibut PSC, but they would only impact their ground fish by up to 3.5%. Now I say only impact up to because in most economic analyses of foregone catch, we don't think of catch in an area as being foregone because those vessels have the ability to move and harvest that catch in other areas. So we call that at risk. So 3.5% of their fish is at risk of not being harvested, but they save 11% of their halibut. Same is true if they avoided both tier one and tier two areas. They'd avoid 22% of their halibut. So, actually, before I go on, I also put the species here and the individual species that were impacted. And you'll notice that, yellowfin sole and rock sole, flathead sole, and peacod, they all don't seem to have much of a difference in how much they're impacted by those closure areas. However, arrowtooth and Kamchatka flounder do. If they were to avoid tier one areas, they would put at risk 30% of their arrowtooth Kamchatka flounder. That brings us to the next further analysis I did, which was, does the fishery influence the hotspot? In prior analysis I've done, we've realized that halibut rates are higher in some fisheries than others, and arrowtooth flounder is one of those fisheries. So I took each grid and I determined what the predominant flatfish species was for each grid using some logic statement. And then I was able to run the hotspot analysis using only those grid cells that had that predominant species. So this is what the map looks like by predominant species. So that yellow is where yellowfin sole is primarily harvested. And we're going to focus primarily on purple due to time constraints. That's where arrowtooth flounder. And if you'll notice that kind of overlaps where a lot of those hotspot areas were identified. So I did this for multiple species. And I'm just going to breeze through these real quick and we'll go to arrowtooth flounder. Well, when you get to arrowtooth flounder, you'll notice that when you're only looking at those grid cells that are arrowtooth flounder predominant species there, that Unimac Pass area still shows up as a hotspot, yet that area up north of the Pribilof Islands, up in this area here, does not show up as a hotspot. So if you wanted to fish your arrowtooth flounder and limit the amount of halibut PSC you catch, you'd want to fish in those areas that are marked in blue or yellow here. So then we went into time of year, and time of year largely covers when fisheries occur. And this figure here shows when the predominant, fisheries occur. Purple being rock sole, and then they move into yellowfin sole. And then during those summer months, when the halibut move to shallower waters, that's when they get into the arrowtooth flounder fishery. So this figure is a little hard to read, but it shows that throughout the year, those hotspots still show up. So if you're in January, February, Unimac Pass, that's primarily a rock sole when they're in that area. Then you move into April and June, still Unimac Pass and up in the Pribilof Islands area. Then July, September, well, they don't fish down in this area very much, but that Bristol Bay area that was identified shows up. And then October, December, it's back down to Unimac Pass. I also did an analysis I'll briefly touch on, and just basically looking at the sensitivity of the search distance and the identification of hotspots. And the star there is where the peak, I ran the final version to identify the halibut avoidance areas. But you notice those areas that we've identified show up no matter what search distance I use. However, some of the more local hotspots wash out when you get up into the 70, 80 kilometer search distance. So in conclusion, we know that we can assign observer point data to a grid with a spatial join, and that can approximate the spatial location of groundfish catch. That various grid cells can be used, and the proper grid cell size should be carefully considered based on the data. Are you looking for local hotspots, or are you looking at a more global area? That GEDIS-ORD GI star hotspot analysis rates can be analyzed to find where high PSC or where PSC rates cluster and allow the creation of halibut avoidance areas. And that halibut avoidance areas may allow vessels to reduce halibut PSC with limited impact on groundfish harvest. Finally, question.
So before you continue, just to repeat the question was, is Josh using observer data? And if there was PFC... Is there unobserved catch data up there also? Is there unobserved catch data up there also?
So it's a pretty good question. So I used observed data for this fleet primarily because this fleet is 200% observed, and that's the term we use. That means that every single one of those 23 catcher processors have 2 observers on board at all times, and they observe every single haul. So I have every single fishing location with the associated biological information for all fishing activity from 2008 to current.
You're using hotspot analysis. Is that the general term, or using geostatistical reading?
So the question was, he saw that he was using only hotspot analysis, but the question is whether any geostatistical kriging was used.
So to answer that question, you know, I used hotspot because I was looking for those areas that had higher rates, right, in relation to the other population, where when you're using like kriging or one of those type things, you're looking as a prediction, I believe, where a certain, you know, you're trying to predict what a value would be. Where I was, the purpose of my study was more to identify where those high rates are. So I believe hotspot analysis was the more proper tool to use.
Any additional questions here in San Diego? Do you have any questions online? And remember, if you have any questions, to unmute your microphone. Or you can also send either Michael or myself your question via the chat in WebEx.